So our first presentation of the day is titled Combined Approach for Integrity Assessment of Welded Joint with Multiple Defects by myself and my colleagues from the Faculty of Mechanical Engineering and the Innovation Center, our Innovation Center. And so basically we all know that presence of defects in welded joints is almost impossible to avoid, and some of them can cause serious issues, and in typical practice, usually only one defect is observed at a time. But we started asking ourselves the question, what would happen if there were multiple defects present, like combinations of different defects, which also actually happens in reality, because certain type of defects can lead to other types. For example, vertical misalignment between the plates can result in undercuts, excess weld metal, incomplete root penetration, etc. So we started developing a combined method which relies on the experimental approach, the digital image correlation, and numerical simulations. And the reason why they're displayed like this is because this time we often made numerical simulations first and then validated them with the experiment, and not the other way around as we usually do. It started with some very simple models a very long time ago, and a couple of years back we started to deal with this topic again because my colleague and friend, Dr. Mihajlo Aranđelović, was working on this as his PhD thesis. So this is pretty much all of his experiments and our numerical simulations. And here you can see a brief overview. This will be a chronological representation of what we have done so far. You can see various stages here, from some very simple models here to the left, to the 3D models on the right, and the examples of the experimentally tested specimens, which we used for comparison purposes. So here is the first paper from the bygone era of 2015, when we made some very simple simulations. Here you can see that there are multiple defects present, vertical misalignment, and that corner there on the left, that's where a very small crack was introduced in the form of a small hole, not an actual crack. And here the goal was to just see how much these defects, how much stress concentration these defects can cause. And you can see here, in one example, we have 158 megapascals, in other 276. But the stresses that were acting in this, well, the joint were around 150, so 15. So in both cases, there was an increase, and the left one was much worse. It almost increased the stresses by 2.5. So this should just give you the idea of how much geometry resulting from defects can actually cause stress concentration and decrease the load bearing capacity. So now for the part about the PhD research, it all started with the joints made of common structural steel S235 with VAC 60 as the filler material. You can see the mechanical properties here, and you can also see an example of some of the models. Here you can see several defects like the undercut, the excess weld metal, and the misalignment. We had 4 total groups, but I don't have enough time or space to present all of them. We want to determine which of these is actually the worst from the structural integrity standpoint. And here, now for all the numerical models, the boundary conditions and the loads were always defined in the same way. One part of the specimen is fixed, and the other one got a pressure applied, which was calculated based on the expected forces or from the experiment. This was the case for, although in this case, you have to be very careful which side is fixed and which side is subjected to the load, because if you turn it the other way around, you can get very different results because of how the tensile test machine will grip the specimen and how it will deform later, because we had some very interesting results, which I will get to later. And this is an example of the finite element mesh that we made. In all cases, we tried several times until we got the finite element size that ensures convergence. This is the simplest version. It only has the material properties for the parent metal and the weld metal. Later on, we would also add the heat affected zone. And you can also see the example of the test specimens themselves. So now for the second round, we decided to make things a little bit more detailed. For example, if you look at the mesh on the right, you very careful, you may notice that the higher plate is a bit sloped, not straight like it was in the first approximation. So we actually introduced the geometry of defects in a lot more details. You can see the measurements that we got. And here you can see some of the comparison of the numerical and experimental results. The numerical simulations were done first, and on the left, okay, this is mirrored, but you can see the stress concentrations exactly where the cracks started to form. And this was the case for most of our examples, except for the one you can see here, because here the crack had occurred in the weld root, but on the opposite side. Now, usually this doesn't happen during numerical simulations, so we had to figure out what exactly was wrong. And the first thing that came to our mind based on our experience was that perhaps all of these defects that we have intentionally caused during welding could have produced more defects inside of the welded joint itself. We were only focused on the surface. So we suspected that the problem was a lack of fusion due to a specific welding position and unorthodox heat input, and that this would decrease the load-bearing cross-section on the other side of the weld root, causing it to fail, even though the crack should form on the left side. And after performing the fractography, this was actually confirmed to be true. So now we knew that for any future research, we should also pay attention to potential lack of fusion. Although for the stronger steel that we used later on, this was not that much of an issue. The lack of fusion was usually less than millimeter. Here it was almost 4. And it didn't affect the results. But in this case, this is an interesting example of how numerical simulations can actually help you indicate the presence of certain defects that you cannot see without using volumetric test methods or fractography. So, and this is particularly interesting because we did not have the means to determine the mechanical tensile properties for the heat affected zone. So we decided to improvise, and basically we would use the results that we got experimentally by digital image correlation. This is the distribution of strain, and then we would try to iteratively guess the yield stress and tensile strength in the heat affected zone that would give us a numerical result which resembles the ones obtained by digital image correlation. And in this case, it was also important to note that knowing about the material you're using is important because it can help you get some idea of where to begin. So after several attempts, we were able to accurately determine the tensile properties, and you can also see that there is a good agreement in the results if you focus, of course, on the parts where the stress concentration is highest and where we expected cracks, although these images are again mirrored. And then from that point onwards, we will continue to use these as input parameters for the heat affected zone. For the weld metal and the parent material, we already had experimentally determined because that was a lot simpler. And here you can see a table which shows the overview of all 4 groups. And this is the stresses, highest stresses located in the vicinity of the defects. We also made a model that didn't have any defects, and we wanted to compare to see how this would be affected. You can see in certain cases, even the presence of defects actually decreased the levels of stresses, which was mostly caused by undercuts in the misaligned models, but the misaligned models were shown to be the most critical ones, as you can also see here from the table based on the stress concentration factors. Now our next stage evolved, including the cracks in our calculations using the extended finite element method options. We would locate the cracks where we expected them to occur during the experiments and where ultimately they did occur. One of these was specific. It's the one on the upper right, because in that case, in all cases, the crack would usually follow the fusion line. But in this case, it just deviated towards the parent material, and we're still not sure what caused this, but everything else had shown very good agreement. We also varied the crack sizes and would apply the loads, which would cause our models to just enter plasticity. And we would also compare that to the digital image correlation images that correspond to the same moment. And here you can see the results for different cracks. If you Here you can notice how every crack from its initial stage tends to move towards the weld metal and the fusion line. And if it would reach the fusion line at that point, the calculation would stop, but the final crack lengths corresponded somewhat well to what we obtained experimentally. And for the second case here on the right, you can also see that the crack has started blunting, which also happened during the experiment. And here you can also see the results for the other two groups with the misalignments. In the last case, the 3mm crack, there was no need to do the 3mm crack because we wouldn't get any result. It was already, and would already enter plasticity by default, which is also something that happened during the experiment. But once again, you can see the tendency of the crack to move towards the fusion line and the weld metal sections. And of course, at one point, it was time to switch to the 3D models for two reasons. First, a couple of years ago, we were talking about this subject that one of the ECFs, I think, and Professor Filippo Berto pointed out that with such asymmetry and geometric irregularities, we will probably have not only have axial stresses, but stresses perpendicular so to the direction of the force. So we decided to see just how much, what part of the axial stresses these represent. So, and more important reason for the 3D models was to prepare them for fatigue crack growth simulations, since ANSYS requires it to be in 3D. So anyway, we just added the thickness. This didn't affect the stress distribution along third. It is plain strain state anyway. And yes, indeed, the stresses along the vertical axis, which is the y-axis in this case, were a lot higher than you would normally expect. With usual symmetrical welded joints that don't have any geometric imperfections, you would have very low values. But here you see, for one of the cases with the misalignment, we had stresses that reached almost 200 megapascals. And in the second case, they were above 300. So it was 40% and over 65% of the equivalent stresses, which is a lot more than you would normally expect. Although in certain cases, some of these stresses were compressive. So they were actually useful in decreasing the stresses. And that's, for example, the reason why the stress concentration factor around the undercuts in these models was less than 1. But this is also an interesting topic, which we will also discuss in more detail in the future research. And we also started recently working on fatigue crack growth simulations, although this is purely scientific. If you see a combination of defects like these, and in practice, you're never going to let that be subjected to cyclic loadings for obvious reasons. This time it was ANSYS, and we used the smart crack growth option. We just wanted to compare to see how each of the defect combinations affect the fatigue life. And of course, we also, on the right, you can see the model without any defects, just a regular one. In this case, we couldn't use different mechanical properties for each individual region, so we just went with the heat affected zone properties. And okay, we didn't have the Paris coefficients, so we used the literature values, but this is only for comparison purposes so far. Real experiments will come at a later point, hopefully. And here you can see how the crack had propagated. It had an initial length of 1 millimeter, which you can see here. And you can see how it propagated straight up towards what would have been the weld metal once again. And here you can also see the fatigue life diagrams, crack extension versus the number of cycles. In the case of the welded joint with no defects, it was over 900,000 cycles. In the other two cases, it was 30,000 and 17,000. So it was a decrease by like 30 times to over 50 times. So if you're ever inspecting welded joints and somebody tells you that welded joints like these can work under cyclic loads, just show them these results to shut them up. And this is something we are working on, well, currently. It's a very similar story, but different materials. This is a combination of stainless steel S304 and structural steel S355, which were also welded. So now we're trying to apply our methodology to this, which is going to be particularly interesting because not only do we have two different materials, we have two different heat affected zones between them. And we also use the methodology I described earlier to obtain these values. And what's also interesting about this combination of steels is that the stainless steel has somewhat lower yield stress, so it will enter plasticity sooner, but it can deform up to like 50–60%. So the other material, the structural steel, which will enter plasticity later, will be the first one to fail. And you can see this, the gray value here in the corner, that corresponds to the experimentally obtained force at failure, which occurred in the structural steel, not in the welded joint or the fusion line, but a bit further away, just like what we have obtained. Now we're going to continue working with these. This one didn't have any defects. We are planning to add some later on, but that's still ongoing. So as for the conclusions, we've already seen that the presence of multiple defects has a significant negative effect, like a lot more than the sum of its parts, and that certain combinations, of course, are much worse than others, especially since they are often encountered. Now, people often tend to get confused and believe that because of these defects, the mechanical properties of the used materials degrade, but that is not the case. The yield stress and tensile strength will still remain the same. It's just that you will need significantly less force to cause these stresses because of stress concentrations resulting mainly from the geometry. And all of the results were verified by combining experiments, digital image correlation, and finite element method simulation. So you can get a lot of valuable information about, in terms of the stresses, where you can expect the defects to occur and to know just how bad the situation could potentially get. And the previously mentioned iterative method for determining the mechanical properties of the heat affected zone is pretty much the biggest innovation and contribution of this approach. And it has shown some pretty good results, although this is only the backup version. The best idea would be to use the micro specimens from the heat affected zone, but if you don't have the time or resources to do that, our method can cover this issue quite well. So this methodology, of course, can apply to different geometries of the welded joints, different combination of materials, just like we saw, with lots of results, stress distribution, concentration. We can also analyze the crack growth as well. And of course, since we can never have enough of these structural integrity analysis, we plan to, in the future, to combine it with fracture mechanics, mainly using failure assessment diagrams. But if we continue with the fatigue, we can also observe the stress intensity factors and whatever else comes to our mind. So thank you for your attention. Since I cannot ask myself any questions, if anybody else has,